In the previous video, we have seen comparison test and examples on comparison test, and we have discussed in the example how the comparison tests are useful to discuss about the convergence of a series. Here in this video we see about Cauchy's root test and D'Alembert's ratio test of convergence of infinite series. So firstly, I am going to write here the Cauchy's root test, statement of the Cauchy's root test. The statement of the Cauchy's root test is if summation un is a positive term series such that limit of un whole raised to 1 by n equal to 1 as n tends to infinity, then the series number 1 converges, then the series converges if L less than 1 and diverges if L greater than 1. And number 3, the test fails to give definite information at L equal to 1. So this is the statement of Cauchy's root test. Why we have called it as a Cauchy's root test? You can see that we have taken the nth root of the term un. So let us see the case first, that means when L is less than 1. If L less than 1, here we choose epsilon such that epsilon greater than 0 such that L plus epsilon is less than 1, and let us call this L plus epsilon equal to alpha. For simplicity we have taken. So what is given, that limit of un raised to 1 by n equal to 1, and therefore limit exists, we can apply the definition of limit. For epsilon greater than 0, there exists positive integer m such that for all n greater than equal to m mod of this term un whole raised to 1 by n minus L is less than epsilon. Okay, so here limit n tends to infinity, this is a L, limit n tends to infinity un raised to 1 by n equal to L. So by this definition of limit we have this term un whole raised to 1 by n minus L is less than epsilon. Now you can see that this limit of un whole raised to 1 by n equal to L, then we can apply the limit, that definition of limit, and you can see that for epsilon greater than 0 there exists a positive integer m such that for all n greater than equal to m, this term mod of un raised to 1 by n minus L is less than epsilon, and it is less than epsilon. This is a positive integer exists because of by definition of limit. Then L minus epsilon, by using the modulus property, L minus epsilon less than un raised to 1 by n less than L plus epsilon, which we have taken it as a alpha. Then now consider this inequality here un and this one, this first part of this inequality, and we take the nth power of this. So if we take the nth power of this will be un is less than alpha raised to n. Un is less than alpha raised to n. This is for all n greater than equal to m. But here we can apply here, this is a geometric series, alpha raised to n. We have taken alpha is less than 1, and geometric series is convergence for alpha is less than 1 and divergence for alpha is greater than 1. Now we can apply comparison test, and by comparison test, if this series is a convergent, un is also convergent. Hence here this geometric series is a convergent series, therefore un is also convergent by comparison test first. Now consider the case second. In the case second, here if L is greater than epsilon, so we choose this epsilon greater than 0 such that this L minus epsilon is greater than 1, and we call this L minus epsilon as another number, suppose beta. Again by the definition here, for epsilon greater than 0 and in the limit we can see that here beta, that means here beta means L minus epsilon is less than un whole raised to 1 by n is less than L plus epsilon. Okay. Then consider the second part of this inequality, this part of this inequality. So what we get here, beta is less than un raised to 1 by n. Now taking the nth power on both sides, beta raised to n is less than un. But here beta is greater than 1, beta is greater than 1, and beta by geometric series, this if beta is greater than 1, this series is a divergent series. Again the comparison test come into power, or we can apply the comparison test. By comparison test, if this beta is this series is a divergent, this is also divergent. So here beta raised to n is a divergent series, and hence this un is also divergent. Hence we have the series summation un where the nth root of the limit un is equal to L is converges for L less than 1 and diverges for L greater than 1. Now let us check what about L is equal to 1. Now we prove by taking examples, counter examples. You can see that suppose we have two series, one is 1 by n, summation 1 by n, and another is summation 1 divided by n square. Suppose this is my un is equal to 1 by n. If we take the limit of this un raised to 1 by n, this is equal to limit, suppose I am going to take the limit of this term, limit of this 1 by n whole raised to 1 by n tends to infinity. So this is equal to 1, as this becomes 0. So this is 1, this is here we get 1. Now see what about the Vn equal to 1 divided by n square, and again limit of Vn as n raised to 1 raised to Vn raised to 1 by n, then limit of 1 divided by n square whole raised to 1 by n is also equal to 1. Okay, here limit of both these term is equal to 1. But look at these two series Vn and un. Vn is a convergent series, but un is a divergent series. and therefore this test failed to give a definite information where L is equal to 1. Now see another test, that is D'Alembert ratio test. So it is similar to Cauchy's test, but that is simple than Cauchy, since here we have taken the root, and in the D'Alembert test UN is a very simple. So before that, let us take examples of example on Cauchy's test. Suppose test the convergence. If we want to discuss about the test the convergence of the series 1 plus 1 divided by under root of n minus n raised to 1 by 2. This is a minus, or you can take this minus as a whole raised to minus 1, whole raised to minus 1, this instead of this. So here what is un? Un equal to 1 divided by 1 plus under root of n whole raised to under root of n. This is my under root of n. Now here un whole raised to 1 by n, whole raised to 1 by n. Here this is 3 by 2, this is 3 by 2. So here n raised to 3 by 2, n raised to 3 by 2, you can see the n raised to 3 by 2. Then un raised to 1 by n is equal to 1 divided by 1 plus 1 divided by under root of n. Here n raised to 3 by 2, 3 by 2, and here 1 by n. Then 1 by n and this 3 by 2. So you can see that this power, here you can check this power, this is equal to n raised to 3 by 2 into here divided by n. So this is 1. So this will be base is same, and subtraction of indices. So this will be 3 by 2 minus 1, 3 by 2 minus 1. So this will be 1 by 2, n raised to 1 by 2, and hence here the series is 1 plus 1 by under root of n whole raised to whole raised to n raised to 3 by 2, right? Then we get here this will be un raised to 1 by n, this is equal to 1 divided by 1 plus 1 divided by under root of n and whole raised to root n. Now let us take the limit of this, limit of un whole raised to 1 by n equal to limit of 1 divided by 1 plus under root of n whole raised to under root of n, n tends to infinity, n tends to infinity. Now look at this, this is e, 1 by n whole raised to n. So this is a limit e, and hence this is 1 divided by e, and 1 divided by e is less than 1. As 1 divided by e is less than 1, the series is a convergent series. So this series is a convergent series. Now let us see the D'Alembert's ratio test. D'Alembert's ratio test. D'Alembert's BERTS, D'Alembert's test. Okay, it is also called as a ratio test. In short, you can use the word ratio test, and we shall mean that it is a D'Alembert's ratio test, because here the term of the series are in a ratio. Now see the statement of this D'Alembert's ratio test. If summation un is a positive term series, positive term series such that limit of un plus 1 divided by un equal to L as n tends to infinity, then the series number 1 converges if L less than 1, number 2 diverges if L greater than 1, and number 3 test fails at L equal to 1. So this is the ratio test, because you can see that we have taken the limit of a ratio un plus 1 divided by un. So consider the first, as it is a proof is very similar to like the Cauchy's test. If you know very simple proof of Cauchy, then we can you can easily apply that to prove the D'Alembert ratio test. So similar to like here we choose this L plus epsilon is equal to alpha, and let us choose it as a less than 1. Okay, so here what is it given? Since limit of un plus 1 divided by un is equal to L as n tends to infinity, by limit definition for epsilon greater than 0, there exists a positive integer m such that this mod of un plus 1 divided by un minus L is less than epsilon. Now this is for all n greater than equal to m. So applying the property of modulus, we get that L minus epsilon is less than un plus 1 divided by un is less than L plus epsilon, which is we have taken alpha, and this is less than 1. Now consider this part, un plus 1 divided by un. Now let us calculate um divided by here we calculate un divided by and you can see that we write this as plus 1 divided by into plus 2 divided by plus 1 dash 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 un divided by un minus 1. Here this term plus 1 divided by so this is less than alpha. Okay, so this is less than alpha, this is also less than alpha, every term is less than alpha, but how many alphas? N minus m times alphas. Okay, so we get that un divided by is less than alpha raised to n minus m, right? Then un is less than, we write in the simplified form as a divided by alpha raised to m into alpha raised to n. Now see this term, this is a fixed quantity, is a fixed term, alpha raised to m is a fixed, here n is a varying, right? So it is like a k into alpha raised to n into here un is less than. Again we can come to the comparison test, and we can apply the comparison test. Here this is a geometric series, convergent series, since alpha is a less than 1, and hence as this series is convergent, un is also convergent. Okay, so here un is a convergent series whenever L is less than 1. Now see the divergent part of this series. You can see that how we have this proof of this series is similar to like the Cauchy's test. Similarly, here we choose this epsilon is such that L minus epsilon is greater than 1. Okay, so we choose this term like L minus epsilon is equal to beta, and beta is greater than 1. Again here limit of un plus 1 divided by un is equal to 1. So for epsilon greater than 0 there exists a positive integer such that this mod of un plus 1 divided by un minus l is less than epsilon for all n greater than equal to, for our convenience if we take it as a different term m1, so this is greater than equal to m1. Now from this limit we have this L minus epsilon is less than un plus 1 divided by un is less than L plus epsilon. But here we have taken this term as a beta, so beta is less than this one. Now similarly let us take un divided by um1. We write it as a um1 plus 1 divided by um1 into um1 plus 2 divided by um1 plus 1 dash 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 un divided by un minus 1. But this quantity is less greater than beta, so it is greater than beta, greater than beta, greater than beta. How many betas? N minus m times betas. Okay, so un divided by here un minus m1 times um1 is greater than beta raised to n minus m1, or un is greater than um1 divided by beta raised to m1 into beta raised to n. These are the this is fixed quantity k. Okay, but this is a geometric series, divergent series, and hence by comparison test this series is as diverges, it is also divergent. Okay, so this is a divergent series. Now see how this test fails to give definite information at L is equal to 1. Again come to our familiar series that is the familiar series 1 divided by n and 1 divided by n square. You can see that here 1 divided by n, this is my un, then un plus 1 divided by un equal to un plus 1 n plus 1 into this n goes into n divided by n plus 1. If vn is equal to 1 divided by n square, then vn plus 1 divided by vn is equal to n divided by n plus 1 whole square. Now let us take the limit of this un plus 1 divided by un as n tends to infinity. So this will be limit of n divided by n plus 1 as n tends to infinity. This is same as limit n tends to infinity 1 divided by dividing numerator and denominator by n, we get 1 in the numerator, 1 plus 1 divided by n. As n tends to infinity this will be 0, so we get limit it as a 1. Similarly limit of vn plus 1 divided by vn as n tends to infinity, so this is equal to limit of n divided by n plus 1 whole square as n tends to infinity, it will be 1 square is equal to 1. So in both the cases we can see that we get the limit as a 1. But look at this series, summation 1 by n is a divergent series, whereas summation 1 by n square is a convergent series. Hence this test fails to give a definite information at L is equal to 1. So friend, you can see, we have seen that how these two series are important, how the proof of the two series, first one is a Cauchy's test and second one is a D'Alembert's ratio test, and one example regarding the Cauchy's root test where we have tested the convergence of a series.